Welcome to this explainer. Okay, so there's this quiet assumption humming beneath almost everything we believe about the world. It's so deeply embedded in our brains that we literally never notice it. I mean, the idea that things just exist independently. A coffee cup sits on your table whether you're looking at it or not, right? A signal travels from point A to point B and it never goes faster than the speed of light. Objects are totally separate and distance is a real physical thing. But what if I told you that fundamental assumption is just, well, completely broken?
For centuries, that assumption wasn't just some abstract philosophy. It was hardcore physics, specifically classical physics. We usually categorize this neat little package under the term local realism. Built mostly on the shoulders of Isaac Newton, this concept describes a universe that acts like a giant, predictable machine. Realism basically means a particle has a specific position whether you bother to measure it or not. And locality means nothing can influence anything else faster than the speed of light. Causes have to physically travel through space over time. So under local realism, every single object has a definite position, a definite speed, and a totally predictable future. Reality is stable, it's local, and honestly, it makes complete sense to our human brains. But then, quantum mechanics crashed the party and completely dismantled that predictable machinery. The cracks really started to show when we began looking at incredibly tiny things, like electrons and photons. Because guess what? They absolutely refused to behave like solid objects. Instead of following clear, predictable paths or settling into definite states, they hang out in what we call a state of superposition, meaning right up until the second it's measured, a particle doesn't actually have a single fixed property. It literally exists as a blurry range of possibilities all at the exact same time. Think about it like this. In our everyday life, if you flip a coin and slap your hand over it, the result is already a done deal. You just don't know if it's heads or tails yet. But in quantum reality, at its most fundamental level, reality isn't made of solid things. It's made of unresolved potentials. That coin is somehow both heads and tails until you actually look at it.
Now, that alone is super weird, but it's really just the warm-up act. The actual reality-breaking stuff kicks in when two of these quantum particles interact. Under the right conditions, when particles get up close and personal, they don't just bounce off each other like billiard balls, they merge. Instead of having their own separate independent states, they get locked into a single shared system. Physicists describe this using a joint wave function. What this actually means is that the particles are no longer independent entities at all. They're just different expressions of the exact same underlying system. And this mind-bending, rule-breaking phenomenon, that is what we call quantum entanglement. To try and wrap our heads around this, people love to use the glove analogy. It goes like this. If you put a left glove in a box and mail it to Tokyo and keep the other box with the right glove in New York, the second you open your box and see a right glove, you instantly know the one in Tokyo is a left glove. Seems simple enough, right? But here is the crazy part. Quantum entanglement doesn't act like those gloves at all. In the quantum version of this, neither particle has a predetermined state while it's traveling. There are no hidden labels inside the box. They are genuinely unresolved, hanging out in that blurry superposition. And yet, the very moment you measure one, the other one responds instantly, no matter how far apart they are. If one is measured as spin up, the other immediately snaps into spin down. Literally zero time passes. This instantaneous connection completely terrified even the most brilliant minds in history. Albert Einstein notoriously called it spooky action at a distance. And he wasn't just being poetic here. This was a severe, fundamental criticism. See, Einstein was basically the ultimate defender of common sense in this scenario. To him, this instant connection was a massive red flag that quantum mechanics had to be incomplete. I mean, if entanglement were actually true, it would imply that physical separation and distance aren't fundamental rules of reality. And he just couldn't accept that the universe would allow for some spooky, invisible influence that completely ignored the cosmic speed limit of light. So, Einstein didn't just casually complain about this, he formally went to war against it. Back in 1935, along with physicists Podolsky and Rosen, he published the legendary EPR paper, arguing for something called hidden variables. And for decades, this was just a really intense philosophical debate. You either sided with Einstein, who demanded a classical, predictable reality, or you went with Niels Bohr, who accepted the quantum weirdness. But then, a massive turning point happened in 1964. An Irish physicist named John Bell managed to translate this entire philosophical argument into hardcore testable math, which meant by the 1970s, we finally had the technology to literally test the fabric of reality in a lab. But before we get to those test results, let's quickly break down what Einstein's proposed solution actually was. To save his beloved local realism, Einstein championed the idea of hidden variables. The logic is actually incredibly straightforward. If measuring one particle instantly determines the state of another one halfway across the universe, and we know absolutely nothing can travel faster than light, then, well, the particles must have already known what they were going to be the whole time. Einstein suggested that they carry these tiny, unseen, pre-written instructions that determine their outcomes in advance. This beautifully explains the coordinated behavior without needing any spooky, faster-than-light magic. It was a very comforting, deeply rational compromise. And then came the 1970s experiments, using John Bell's math. Bell realized that if hidden variables actually existed, there would be a strict mathematical limit to how perfectly these particle outcomes could correlate, a hard ceiling, which we call Bell's inequality. Basically, if Einstein was right, the experimental results could never ever cross that classical limit. But when they actually ran the experiments, the observed quantum correlations absolutely shattered that limit, destroyed it. And it has been violated in every single increasingly advanced experiment we've run since. This proved mathematically, beyond a shadow of a doubt, that local hidden variables simply do not exist. Einstein's comforting compromise was wrong. So, what does this actually mean for us? If particles aren't secretly following a script of pre-written instructions, but their outcomes still correlate instantly across space, we are left with one truly staggering conclusion. The universe is non-local. Non-locality means the whole concept of independent localized objects completely falls apart at the quantum level. Distance literally does not fundamentally separate things. Two entangled particles aren't two independent objects trading invisible text messages. They are components of a single, unified system. At its absolute deepest level, reality isn't built out of isolated puzzle pieces. It's built on interconnected relationships. The very idea of space begins to lose its meaning as a fundamental separator. All right, I know exactly what you might be thinking right now. Let's just pause and look around for a second. Seriously, look at your everyday surroundings. If everything is ultimately a quantum system built on non-local connections and blurry, undefined possibilities, then how on earth does a universe of undefined states create solid things? Why isn't the coffee cup sitting on your desk right now existing in some weird, blurry superposition? How do stable identities and predictable cause and effect rules magically emerge from a foundation of spooky, chaotic quantum weirdness? Well, the answer to why our everyday reality feels so normal comes down to a process called decoherence. You can think of it essentially as the rapid dilution of quantum entanglement. See, a quantum particle rarely stays isolated for very long. Pretty quickly, it bumps into its incredibly messy environment, things like air molecules, thermal radiation, or just general electromagnetic background noise. And every single time it interacts, it gets entangled with that environment. This spreads the original quantum information outward, watering it down and distributing it across a vast, practically infinite web of connections. If you have a perfectly isolated system in a high-tech lab, you get clean, observable quantum weirdness. But out in the real world, you have a decoherent system. Now, to be clear, the system doesn't actually stop being quantum. It just gets way too entangled for us to ever track. Think of it like this. Imagine a friend whispering a secret to you in a completely silent, empty room. That's your isolated system. You hear it perfectly. Now try hearing that exact same whisper while standing in the middle of a massive cheering stadium during a rock concert. The original sound waves are technically still hitting your ear, but they are entirely swallowed up by the background noise. Constant environmental entanglement basically washes out all those spooky quantum signals. And that right there is exactly why your reality feels normal. Entanglement isn't some super rare occurrence. It is absolutely everywhere. Everything is constantly bumping into everything else. But because this entanglement spreads so incredibly fast across billions and billions of particles, it all just averages out into stable, classical behavior, which leads to a pretty wild realization. The classical world, the world we see and touch, isn't some separate, distinct layer of physics. It's literally just the simplified byproduct of entanglement spreading way beyond our human ability to observe it. The boundaries you see between you and the objects around you, they aren't fundamental divisions of the universe. They're really just incredibly useful approximations. This complete inversion of how we think reality works creates some serious, mind-bending psychological tension. As physicist Leonard Susskind points out, in classical, everyday thinking, reductionism always works. If you want to understand how a car engine works, what do? You break it down into its parts. If you figure out the parts, boom, you understand the whole engine. But quantum entanglement completely shreds that logic. In a quantum system, the whole contains information that the individual parts simply do not have. You literally cannot understand a quantum system by breaking it apart, because the individual pieces remain entirely undefined until they are actually measured. This is exactly why this topic makes our brains feel so itchy and uncomfortable. It hits the absolute hard limit of human intuition. I mean, think about it. Our brains evolved to survive in an environment of large, slow, local objects. We evolved to dodge flying rocks and hunt for food, not to calculate quantum wave functions. Our biology relies on classical shortcuts that prioritize keeping us alive over calculating absolute fundamental accuracy. We naturally seek clarity by dividing things up and keeping them separate. So when quantum mechanics operates by a completely different set of rules, our intuition doesn't just fail to help us, it actively gets in the way of us understanding physics. Our inherited mental software just wasn't built to visualize actual, fundamental reality.
Which brings us to our final thought for this explainer. What if the stable, predictable reality we experience every day was always just the surface? Quantum entanglement doesn't mean our reality is broken or glitching. It just means the mental model we inherited was never actually built to describe the universe at its deepest, truest level. It forces us to accept something profoundly humbling. The universe is under zero obligation to match the way we happen to perceive it. We live in a universe defined by relationships, not just isolated objects. A universe where separation is kind of an illusion, and where we are all far, far more interconnected than we ever could have imagined. Thanks for joining me on this explainer, and keep questioning the surface of your reality.